I got here early, so I had a minute to sit and partner up for a minute. So okay, today we're gonna go through Tully Fisher and all that stuff. Uh, so there's the readings. I'm gonna go quickly through a couple of them. The running theme in the reading question was, "What's this fundamental plane?" I don't understand that. So we'll spend some time talking about that. And actually, uh, it's kind of cool because I'm going to talk today about machine learning, which I've never done before. Um, because there's this process called principal component analysis that is kind of been consumed by the machine learning idea. So it's now a machine learning idea, but we'll talk about how it works. It's a clustering algorithm. It's a way to describe how things cluster. So um, so we'll talk about that, and so I'm not actually going to say anything about most of these today because I'm going to cover them when I go through the lecture. So let's see. And where was I at? See, I started talking about these, and let's see. We said ellipticals aren't just. Let's see. Yeah, I think I was here. Does anybody remember how far I got up here? Anyway, let's start talking about this one. I don't remember if I said anything about do non-luminous galaxies exist. Did I talk about this last time? I don't think I did.
I think we did
yeah.
briefly.
Okay.
Because don't they like exist but really hard to detect?
Yeah. Okay. Cool. Yeah, it was at the end of class, and my brain is kind of winding down. So non-luminous galaxies exist, but they're hard to see. I mean, anything that's small is going to be dim. So there are a handful of low-mass galaxies around the Milky Way, and we can see those. We're starting to be able to see those better, but around other galaxies, they're really hard to see. So around Andromeda, we can see a couple, but so by non-luminous, I mean not very luminous. There might exist galaxies that are totally dark and just balls of dark matter. Sometimes we can see naked balls of dark matter. But not very many. So there are a couple of blobs of dark matter that we have found that we know here is a blob of dark matter, and we also can see that there's no stuff in it. There's a couple of those, but they're massive. They're very, very large objects. There might be little ones, maybe not. Hard to say. So the low mass end, we're not real we've got theories that describe things, but that's where things get dodgy. Okay, are we able to tell what kind of galaxy a forming galaxy will turn into? I don't think so. I'm not able to. But you can kind of. So basically, the way galaxies form, I guess I haven't drawn this picture yet. Let me talk about how galaxies form. For the most part. So now JWST is throwing off my story. So and this is something that my plan is to get into in the next couple of days, is to go figure out what JWST is saying is wrong about all the stuff I'm going to tell you. But that's all real fresh science. For the most part, you start off with very little fluctuations. And on those fluctuations are other fluctuations. So you got a superposition of fluctuations. You got some long wavelength modes and some short wavelength modes. Really, there's a hierarchy. I drew two on here, but there's a whole spread of modes. But you get some big modes and some little modes, and the little modes can grow. The big modes can grow. Everybody grows. This one gets lower, and this one gets higher, as this one sucks up all the stuff from that one. So as this thing gets denser and denser and denser and denser, eventually it will find the thing next to it and it will merge. So things get denser and then they start to merge and crash into each other. So you get you get a whole bunch of little things that then merge into bigger things. You can't do that. So these guys will merge, and then these guys will merge, and these guys will merge. And we have this process of hierarchical merging where little things merge with other little things, and then they merge into bigger things, and clusters of stuff merge with other clusters of stuff, and in that process other things merge. So there's lots of mergers where little things smash into each other and form big things. The biggest things are big CD galaxies, and these are like 10 to the 13 solar masses, and they're elliptical galaxies. Slightly smaller than that, we have big ellipticals and big spirals. So around 10 to the 12 solar masses, you have very large spirals, but also ellipticals. So it's hard to say, and you probably can if you understand the angular momentum well enough. So if you understood all the angular momentum, sometimes you get a whole bunch of mergers that wind up making a disk galaxy. Sometimes they make an elliptical galaxy, depending on the phase of the angular momentum. So it kind of depends on the angular momentum. Yeah. Also, it's a chaotic process, and we don't understand it super well. Let's see. Unclear about what the fundamental plane is. Tilt of the fundamental plane. We'll get to those. Which Tully Fisher is typically used? And that's two questions. The infrared one, most often. The infrared observations are usually the best ones because the dirt is in the way for the optical observations. Optical observations are tricky. Is constant mass to light normal? No, it's what you want to be the case. I want galaxies to have constant mass to light, and spiral galaxies seem to have average mass to light that is roughly constant in the interior surface brightness, in the interior. So the central surface brightness has relatively constant mass to light, but it's not normal. It's just an assumption that you need to make sometimes. Are there other relations implied by these things? Yes, probably. Not that I know of. I'll talk about d sigma. What's the evidence for dark matter in ellipticals? This is the same idea that we were talking about with spiral galaxies. We have that v squared equals gm over r. So this is kind of a stem cell of an equation because I turn it into other things. So this v isn't pretty well defined, and neither is m, and neither is r. When I write it down like this, this is just I'm waving my hands and write down virial theorem. So we turn this into things, so we can say that the circular velocity squared equals g times the mass interior over r. This is good for spiral galaxies, where I'm now defining this as the circular velocity. This is going around. And this is now the mass interior to a point r at a radius. So we can see that this circular velocity is related to the mass. That's one thing I can write down. I can also write down that the velocity dispersion squared is equal to g times m over r, which is a similar idea. I just have velocity squared. Now we're talking about the random component of the velocity. That squared has got to equal gm over r, because this is the energy containing term, is the random component. So we do a similar stunt. We say, I know what sigma luminous is from measuring the light, and I know what sigma total is from measuring the velocity, and that gives me what sigma, so I know what sigma total is from measuring the light. I know what sigma is from measuring the velocities. I know what sigma luminous is from measuring the light, and the dark matter has got to be whatever I'm missing. So evidence looks kind of like that. Why is the slope 4? I'll show you. Why does 21 correspond to 2 Vmax? Vmax is going one way, this way, and this way, this way. So if you're going around with velocity v, then I'm coming at you with a velocity v and going away from the velocity v. That difference is a velocity of 2v. So you find out what v is. This makes more sense when I point at a graph. When the text says dark halo, does it mean the dark matter outer parts of the galaxy? Yeah, so a galaxy is a big ball of dark matter, and in it is some stars. A galaxy cluster is a bigger ball of dark matter, and in it are some galaxies. So we get these spheres, roughly spherical, round regions of dark matter, and inside are galaxies. And sometimes they run into each other. Sometimes you have smaller blobs of dark matter inside. Yeah, when it says dark halo, it means the dark matter outer parts of the galaxy. Yeah.
So it's like a full sphere, not just like a ring.
Yeah, that's right. What's the mass fundamental plane? I'll say it again. What's the importance of the tilt? I'll explain that. D sigma is confusing. Yes, I'll explain that again. These two things, IE and IE, So he talks about IE and average IE. This is the central brightness. So we're going to say that the brightness as a function of R is going to go something like IE times e to the minus R over H. Does that make sense? So that's the central brightness at the center. This one is the average. These angle brackets mean average. So that means add it all up and then divide by the surface area. So they're related, but they're different because this one is just at the center and this one is averaged over the entire thing. More on that later. Do all spirals eventually evolve into ellipticals from mergers? I don't know about all. That is part of where ellipticals come from. But I don't know, maybe this is my own ignorance. I don't know if all spirals eventually turn into ellipticals. I think no. I think that after we're done colliding with Andromeda, we will still be a spiral galaxy. I think the end state of that's still going to be a spiral. And I don't think that we're going to merge with anything else in the near future because there's nothing else close. There's a little crap, like the little galaxies that are orbiting us, but they're not going to change our angular momentum very much. What's the distribution of dark matter for ellipticals? Round, spherical, like a 1 over r squared. That's pretty common. Effective radius is that. These something I'll say that again in a minute. So all of those I'm going to say again. Okay. Any questions other than the ones that I obviously skipped? Yeah.
This is on what you were saying earlier about the massive dark matter that we know.
Yeah.
Is there any that is like that we have to try to phrase this? So you know how like when we look at like supermassive objects, you can see the like bending. Is that how we see that like giant mass?
Yeah.
So it's like you can just see that everything's being warped behind it. So
yeah.
There's obviously something there.
Let me show you a picture of that. So do I have internet? No. Where? I have a good picture of that. There's only a couple of these, but fascinating. Sorry. I didn't do clusters last year. And I'll find you a picture of that later. So there's a thing called the bullet cluster that you can look up if you're bored. And I'll talk about the bullet cluster when I get to galaxies, but galaxy clusters. But the basic idea is there were two galaxy clusters and they smashed into each other. And the dark matter kept going and all of the gas pancaked in the middle. So we see these two big balls. So when we look at the lensing, we look at microlensing, we can measure these two big spheres of dark matter that don't have any gas in it. When we measure the X-ray, we can measure that the gas is right in between the two things. So it's really pretty clear that they just smashed into each other and kept on going. It's kind of cool. Yeah.
So you say that like we've observed giant dark matter objects. Is it like clear, or is there like an extinction effect, like for objects like through it, or can we not see anything past it, or?
This will make more sense when I pull up a picture of it. It's absolutely clear.
Oh, okay.
Like you can't. There's no extinction effects. If there were extinction effects, we could use that.
Okay.
That would be cool. We would love it if there were extinction effects. There's 100% no light absorbed by the dark matter.
Wow. Okay.
Yeah, but you can see that it's there. It's pretty cool. Okay. Other questions? Now I gotta pull up the right display. Okay, so today I'm going to talk about empirical relationships that we don't really understand very well. We're going to wave our hands past them, but really these are all empirical. These are all, I made a plot, I saw this relation, it seems to be robust, let's use it. So that's how all of these work. So we'll talk about Tully-Fisher, which is good for spirals. Then we'll talk about ellipticals, we'll talk about Faber-Jackson and the fundamental plane and D sigma, which all kind of do the same thing. In there, I'm going to talk about PCA. Then we'll talk about the bimodal color distribution again, and then we'll talk about the Schechter luminosity function, which I think I forgot to put in the readings. I think I forgot to make you read the luminosity function section. That's okay. I'll talk about it. I'm not going to make you do much with it. So the Tully-Fisher relationship looks like this. So this is log of the maximum rotational velocity on the bottom and the brightness in various bands on the vertical. So does it get brighter going up or going down? Clearly we've got negative numbers. They're like minus 24. They're getting more negative going up. So these are in magnitudes, and negative is bright. So that's cool. That tells us what this says. And what we see is that the maximum luminosity is proportional to the maximum rotation to some number, which turns out to be like 4. So that's cool. Before I say anything else about that, why is that cool? What can I do with that now? Let's say, for instance, that this is a universal truth, which we'll just assume. Why is this cool? What can I do with this? That is the one thing that I keep saying is hard to do. I can measure distances. How do I do that? What's the first thing I got to measure? Say I got a galaxy, I got a spiral galaxy. It's spinning, I've got a radio telescope. What's the first thing I measure? It's velocity, and I need the maximum rotation velocity. And then what do I get? Luminosity. Which luminosity? If I'm going to turn it into magnitudes, which magnitude would be, the apparent or the absolute? It gives you the absolute magnitude. It doesn't give you the apparent magnitude. That has the distance in it. Right? So, I got my galaxy. It's spinning, rotating like this. So I remember when I had that contour map of all the radio curves. I'm going to measure velocity contours, and this one is going to be coming at me really fast. This one's going to be coming at me not very fast. This is going to be moving away from me not very fast. This one's going to be moving away from me pretty fast. So I make a histogram of the velocity. So I just take all the velocities and I count each one, count how much light I get from each velocity bin. So this is v on the horizontal axis. This is equivalent to wavelength velocity because we know how Doppler shift works. So if I measure this, I'm going to have the bulk of the galaxy. A lot of the galaxy is not moving very fast because we don't see the rotation of the galaxy. If I look here, I only see the mean motion of the galaxy. We take that out, so we call this 0. So we get a bunch of light here. It goes up to the outskirts where usually there's a bunch of light here because you see a lot of column. So we get an excess of velocity at these maximum velocities, and then it falls off. And the same story over here. So I get, it has horns because I see a lot of this velocity that's coming at me. I don't see much velocity here. So it doesn't matter too much. I make a histogram where I'm just counting all the stuff. So this is just a spectrum, and it's just a measurement of how much stuff at what velocity. Make sense? So I take this one and I take this one. I'll call this one V1 and this one V2 and this one V1. V max is going to be V2 and V1. Right? This ought to give you the same number. Okay, they don't really, because we're measuring things, and measurements are hard. So we average these two. And that's just saying V2 minus V1, right? I just take the difference between these two because I know that this one is going in one direction and this one's going in the other direction. Does that make sense? Over 2. So I'm just averaging this. I got to take a minus sign because this one has the opposite sign. So I'm just A plus B over 2. So it's just the width of this. But really, I just care about the width of this. Then, so now I've got V. I know that the absolute brightness in the V band, say, is going to be alpha times the log of V max over V naught. We need some fiducial. I have a log. I can't put anything with units in a log. I can't take the log of a meter. It breaks the world. You can't do that. It doesn't make any sense. So you got to divide by some fiducial when you're plugging into the log, but it doesn't make so you have to do that to make the units work. But this is the part that I care about. This is where the behavior is. So the behavior is that the absolute luminosity is going to go like alpha times log of V max, and that's what we get here. And there's a minus sign there because it goes up as it goes negative as it goes up. So that's kind of dumb. But so why? Let's talk about first. Then, sorry, I forgot where I was going. This gives me the absolute brightness. So the luminosity at the object gives you the absolute brightness at 10 parsecs. It's got to be at 10 parsecs because everything is infinitely bright at 0 parsecs. So this gives us the absolute brightness. Now, what do I have to do to get the distance? I got to measure one more thing, and then I got to do some math. So what's the other thing that I have to measure? I have to measure the apparent brightness. And then what's the thing that I do to get the distance that looks like a magnitude? It's got a distance in the name. It's the distance modulus. So the difference between these is going to be the distance modulus. M minus big N. And then 10 to the mu plus 1 over 5, or however that is, I don't really care. 10 to the mu, there's a minus sign in all those units of crap, right? There's a 5, gives you the distance. What do I care about here? I care about finding a way to get the absolute brightness based on other things that are easy for me to measure. What's easy for me to measure? Radial velocity is easy for me to measure. That's one of the things. These are running themes throughout the thing. Distance is hard, velocity is easy. So we can measure radial velocity, that gives us absolute brightness, which gives us distance. So that's very cool. See, one of these, the infrared one has the least scatter. So there's slight differences in all of these based on the wavelength that I don't know enough to really piece out, and I don't think I have the time to get into the details because I'm sure they're complicated. Really, this is the bit that we care about most. So at 10% scatter is pretty good. You get the luminosity from the rotation, and that gives you the distance. This is the next rung on the distance ladder, because I can do this for things that I can't see very well. I don't have to be able to resolve the galaxy very well. I only need a couple of points across it to get the distance, so I can get this to galaxies that are really, really, really far away. So as far as this works, it does a really good job for getting very good distances. So this is NGC 7331, which is the one galaxy that looked like a cigar that I pulled up the other day with those contours on it. So the width of this curve is twice Vmax times the sine of the inclination angle. That's the angle that it's pointing at you at. So if the inclination angle comes out of the center of the galaxy, like the angular momentum vector. So when that's pointing at you, you see nothing because you don't see the velocity. When that's 90 degrees and the galaxy plane is pointing at you, then you see all the velocities. So you don't have to reduce that geometry. So that sine I is just the geometry of how the galaxy is pointing at you. Okay, let's wave our hands and see how this works, just to get a feeling for the fact that it should work and where the assumptions are that we have to make to wave our hands past it. And I got to be on the right desktop. So, B squared equals GM over r. Here's our stem cell equation. We're going to now write this as V max, the maximum velocity. Why can I do that? Well, what does it imply when I do that? When I declare something about the velocity, it also says something about what mass I have to be using. So if I'm talking about the maximum velocity, we know the maximum velocity is going to be out here because that's how galaxies tend to work. And we know that they tend to be flat out here too. So the max velocity is pretty constant at this outer region. There might be bits that are rotating a little quicker on the inside, but really the max velocity gives you the bulk of the rotation of the galaxy because of dark matter, because I'm not just orbiting this blob here, I'm orbiting this dark matter sphere. So okay, V max equals Gm over R. Rearrange this to get the mass equals V squared max times R over G, right? The luminosity, which is the thing that I can measure, is just 1 over the mass to the light times the mass. One thing that I learned, I was a math major as an undergrad, one thing I learned is that when you're a math major, 80% of your stunts are either cleverly multiplying by 1 or adding 0. It's like half of the stunts is a math, either adding 1 or adding 0 or multiplying by 1. So here I'm multiplying by 1. I mean, though, it's kind of a dumb sentence, right? But that's okay. This is a thing we know. This is the thing we have over here. So this equals, I called this upsilon before, upsilon times V max squared R over G. We now say that the average surface brightness is going to be the luminosity over R squared. So R squared equals the luminosity divided by the average surface brightness. Now we said that from Friedman's relation, the average surface brightness for most spiral galaxies is roughly constant. So this is kind of a constant number. The luminosity changes as the radius changes, so that's cool. So let's square this. So I got L squared equals upsilon to the minus 2 V max to the 4th R, which is L over I over G. Yeah. So does have a G squared in the bottom, and just an average I. Where's my other L go? Oh, I square both sides. This L cancels this L. There you go. Okay, so the luminosity equals the mass to light ratio to the minus 2. Maybe this is constant. It's not really very constant, but it's constant enough. Times 1 over the surface brightness, which is roughly constant. G squared, which we super hope is constant, times V max to the 4th. So there you go. The important bit, so the assumptions that go into Tully-Fisher working are that mass to light ratio is roughly constant. What sets the mass to light ratio? Kind of a dumb question, but there are 2 things that go into it. What are they? There are actually 3 things that go into it. So there's the light. What's that? No, mass to light is integrated over the whole thing.
Oh.
It's just the total light, or the total mass, which is the dark matter and the stars, divided by the total light, which is just the stars. So this quantity depends on the dark matter in ways that aren't really in this equation. This is kind of a dodge, but it works okay. And the other thing is the average surface brightness is roughly constant. If you do that, then luminosity goes like b to the fourth. Cool. All right. Is there anything else that I want to say about Tully-Fisher? Okay. There is one more thing, and now I forgot about this. Sorry, there's a point that I wanted to make about why this works. So the last thing that the book brings up about Tully-Fisher is this baryonic Tully-Fisher. And there's an argument here that I forgot to remind myself how it works. So I gotta go remember how that works and come back to you later. The argument is that this is a demonstration that okay, so what do? So we take the mass to light ratio, or we take the mass and the velocity for a bunch of galaxies, and we see this. And we see these green points, which don't really fit. But if we add all the gas, so instead of just the mass from the starlight, we do a radio measurement and we add the mass of the gas as well, we get a better match, right? So this is a much better match. So this is now the total mass versus the central velocity, and we see that this is a much better spiral. The people who do MOND claim victory with this. I don't know if they really get to, but they do. This is the first time I'm going to talk about this. This is modified Newtonian dynamics. And it's an alternative to dark matter. What it says is that when the accelerations get really low, the force law changes. Why would you assume that? Because we want to get the rotation curves of galaxies correct. The entire purpose of MOND is to get the rotation curves of galaxies correct. And it does a great job because it was designed to do that. So of course it fits. It's got enough free parameters that it can fit whatever it wants. They like to say that this is proof that dark matter doesn't matter, because clearly the dark matter and stars aren't doing all the rotational dynamics. You got to include the low density gas too. I'm not as convinced by that argument. I think it's a dynamics issue. You add more mass and you get a better measurement. But and for low surface brightness things, more of the mass is in gas that's not in stars. So I think just doing the accounting better doesn't really say much. So you guys can totally forget the baryonic Tully-Fisher at this point. Okay, let's do this for ellipticals now. So similarly for ellipticals, we have the luminosity goes like, now the velocity dispersion to the fourth, which is the same kind of argument. Now the energy containing body is the random components of the velocity versus the circular components of the velocity like we have for spiral galaxies. But there's a lot bigger spread, so this is a much worse tool. I want to use it to do the same thing. I want to use it to get distances. But if this spread in this relationship is large, then the error that I get in my distance is going to be large too. This is the same argument. Luminosity goes like velocity to the fourth, though. Oh, I wish I hadn't erased that board. I could just control the thing that I have here. The surface brightness isn't as constant, neither is the mass to light ratio, which is why it does so much worse with with elliptical galaxies, because the assumptions that we needed to make are all the way not supported. So, instead we think about something a little bit more complicated. So we got to fold in more information. So we don't have this constant surface brightness anymore. So we've got to fold in some information about the surface brightness, about what it's doing as a function of size of the galaxy. So here's where I stop, and I don't have anything prepared. I'm just going to improv, but it's going to be good enough because I realized that I needed to do this on my way down the elevator. I was like, oh, I got to talk about PCA. That's going to make this make more sense because that's where this came from. So I'll have more. I might have more on this in a minute, but and I'm skipping the math. So I might have you do something. If we get through all the numerical exercises, I might have you do something with this. But principal component analysis. I have a collection of points in some n-dimensional space. For all of my cartoon examples, I'm going to use n equals 2. So how many coordinates do I need to describe my collection of points? N. So I need n coordinates to describe my points because they live in an n-dimensional space. Unless they live in a subspace of that, then I need fewer coordinates. So let's look at some dumb examples. If I got a collection of points like this, I fully need both components. Let's call these x1 and x2. So these are two parameters that describe my collection of objects. Whatever those parameters happen to be, this is super generic. So this could be age and weight for humans in the United States. That wouldn't look like this. This goes negative, and I don't know what negative age is, and it goes negative in both directions, as I really don't know what negative mass is. But let's say, for instance, that we're looking at, let's use age height as less judgy. If my collection looks like this, then that's relatively hard to describe because I need both pieces of information. But if I'm looking at the age-height relationship, so this is age, this is height, what's that going to look like? Is it going to be a sign? No. It's going to be basically linear, right? Because you basically just get bigger as you get older, right? Up to a point. So let's say this is age for, let's cut this off at 25. Everybody's done growing by the time they're 25 for the most part. So what's that scatter plot look like? So I'm just going to plot age and height for everybody in the United States. I mean, clearly it's going to start at 0. Oops, I'm just changing colors. It's going to look kind of like this. It's going to be a basically linear relationship, right? With some scatter. So how many pieces of information do I need really to tell how tall you are? I only need your age really, and then I got a little bit of error. So I take this two-component family, age and height, and I'm just going to rotate my head and just talk about this. And now I'm going to call this x3 and x4. I just rotated my coordinate system. So now x3, now I don't know what to call it anymore. It's some combination of age and height. So I can't call it anything. It's now my first principal component. And my second principal component, I don't care about as much. Does that make sense? So really what I need to know if I want your height is just your age, and I'll just find out where you are in that coordinate, and then that's basically what your height's going to be. So we can get height from age. There's a scatter, so there's of course going to be error, but there's error in all the measurements that you make. So principal component analysis is taking a cloud of points and finding which axis has the most variation on it, and then lining the coordinate system up with that. So then you can see what's going on. It's about finding the axis the coordinate system that better describes the data. So it's about finding the coordinate system. Does that make sense? So I have this thing, it's got some clear trend. I mean, clearly height and age are related. Clearly there's spread. I get all the 45-year-olds that I know, and I'm not the tallest one. I get all the 8th graders that I know, and my kid is the tallest one, unless we get kids from the other Thomasville school, and they're all taller than my kid. So there's variation, but what is it that you need to know? You only need to know this one, really. What do we do? Why am I talking about this? Why am I talking about age and height? So what I'm going to do for galaxies, for elliptical galaxies, I want a luminosity-velocity relationship. And when I write my luminosity-velocity relationship, I get something that, these are logarithmic axes, I get something that looks like blah. So there's a trend, but there's a spread. But remember what the missing thing is. We have to know about the average surface brightness, because that's not constant anymore for elliptical galaxies. So I have another axis, the average surface brightness. And when I look at all of these things here, I realize that it's not that there's a spread. If I take a piece of paper and look at you, there's not very much spread. If I flip it that way, there's more spread, right? Looks like more. But all I did was rotate the axis. I didn't make the data worse. So now we just need to view the data from slightly up there. Now you can all view the data from this other angle, and you see that this is flat. This has a lot less error. So what we do with the fundamental plane is a relationship. Oh. I can't click on. I have 2 displays, and one of the displays is whatever I'm recording, and I can't click on that window to make that thing do what I want. And I always feel like kind of an idiot when I do that. So, is that the derivation that I have right here? Do I like this math better? Yeah. Okay, so let's go through a little bit more. Let's go through wave our hands through the math again. So mass to light, roughly constant. That's not an awful assumption for elliptical galaxies. Something about their stellar population. What about the stellar population of elliptical galaxies makes the mass to light ratio more constant than it is for spiral galaxies? Less bright young stars. Those bright young stars jack up the mass to light ratio. The old K stars all have basically the same mass to light ratio. So a big elliptical galaxy is basically made out of low mass K stars that all have basically the same mass to light ratio. You don't have these huge spreads in the star formation rate. That being said, the dark matter is there. So mass to light being constant, not a great assumption, not a terrible assumption. This is the one we're running with. We also know that the mass is going to equal sigma squared r. That's just sigma squared equals gm over r. There's a proportional. G is a number, it's got to be there, whatever. Put the G in so that the units work. So mass is proportional to the velocity of dispersion times the radius. So the mass to light is going to be sigma squared r divided by the average surface brightness times r squared. So R, I'm not crazy about writing it this way. Maybe I want to write it the other way. But anyway, is the mass to light minus to the minus 1 times sigma squared times the average surface brightness to the minus 1. Now, before, when I was doing this with Tully-Fisher, as a sigma squared. When I was doing this with Tully-Fisher, this is constant and this is constant, so we just have a relationship between r and sigma squared, or mass and sigma squared. But now surface brightness changes with the galaxies as well. So now I have 3 components to describe my data. So I need to use a slightly more complicated system. So I did have a luminosity velocity plot. Now I need a luminosity velocity surface brightness plot. And we'll put all our galaxies in this 3-dimensional space, and then we'll just rotate our head until we see the one where it looks like a line. Okay, we do math for that, but that's outside of what I want to get you guys to do. And we find this. We find R E is equal to sigma to the 1.4 times the effective brightness to the minus 0.9. How do you define a plane? How do you write down a plane? What's the equation for a plane? That's the sentence I wanted. What's the equation for a line? Y equals. What's the equation for a plane? Z equals. Yeah. Ax plus by plus c. So it's just the same thing. So y equals mx plus b. A plane, z equals mx plus wy plus b. Same thing, just another line. You have another linear part. I did not write a line here. I wrote 3 power laws. We'll take the log of it and turn it into a line. So now we've got the log of effective radius equals the log of equals 1.4 times the log of sigma plus a minus 0.9 times the log of the surface brightness. That's a plane, right? So this is the slope and this is the quantity. Here's the slope, here's the quantity, and here's our vertical axis. So this defines a plane. It's not a physical plane, it's a parameter space plane. So it's in this R sigma surface brightness plane. But it's a plane, and this reduces the measurement. So what do you need to make this work? You also need to measure the average surface brightness. You need to have a measure of the angular size of the galaxy, as well as the velocity dispersion. Okay. Any other questions on that? Does that make sense? Does anybody have any questions on? Yeah.
So the fundamental plan is just for convenience, basically?
Yeah. Yeah, that's it. It's a convenience thing to make it easier for me to describe the galaxies. Yeah, that's it. D sigma. Observers like D sigma. This is the same idea as fundamental plane. except it's relating the velocity dispersion to this average light. So the average size d is an effective radius of the galaxy. It's the radius within which you have a magnitude of like 20. So we have this effective radius that we define, and there's a relationship between that and the velocity dispersion of the stars. Why? Well, because dn, the Holmberg radius, is going to be proportional to, is going to depend on the average surface brightness as well. Because if the average surface brightness goes down, dn just gets bigger. So you bake in some of this. So this part here, this average surface brightness, gets baked into the definition of the radius. So this works pretty well, works better than the Faber-Jackson relation, which I don't know, I don't know if I said Faber-Jackson out loud, because I went by it so fast. Faber-Jackson is just the simplest thing you can do that looks like Tully-Fisher. Fundamental plane is better, and that's what people usually use. D sigma is also better. This is a thing that people use pretty regularly. This is best for elliptical galaxies. Let's see. There's some similar hand waving, but it's the same basic idea. Yeah. So we talked about fundamental plane and Tully-Fisher. Okay, a couple other demographics issues. We talked about this bimodal color distribution, and I'm going to bring it up and drive by it again. So that tells us how mass and velocity are related. This tells us how light and color are related. So we drop all of our galaxies on here, and we find that if we sort them by brightness on the horizontal and color on the vertical, that means redder is at the top and bluer is at the bottom. Brighter is on the left in this one. Dimmer is on the right. We find that red galaxies are brighter than blue galaxies. That's basically what this plot says. We've got a population of big red things and a population of smallish blue things. And if we do some math to try to say, well, okay, which ones of these are spirals and which ones are ellipticals, we have this Sirzik index, which smoothly transforms from a spiral-looking potential to an elliptical-looking potential. And we also have a bimodal distribution in these. So this is color versus Sirzik index. So we have a big blue blob of things with a Sirzik index of 1, which means they're spirals, and a big red blob with a Sirzik index of about 4, which means they're ellipticals. It's kind of a neat measurement. Okay. I gotta make sure that I make you read this section, actually, now that I think about it. So we want to talk about the luminosity function. And the luminosity function is another distribution. And it's the distribution of the luminosity. So to get your head around what this function is, you got to look at the units. So I want to know how many galaxies I have do I have at a brightness L, whatever L is. This is an impossible question. The answer is infinity, because space is infinite. I'll be here all week. So this isn't a question that I can ask. What's the density of galaxies at a brightness L? Because the number of galaxies that I have is directly proportional to how big the volume is that I survey. How big is the volume that I care about? That's the thing that is going to really matter. So I have to divide by the volume. If I double my sample size, I double the galaxy count. So we're going to talk about the density as a function of brightness. And we're going to define this function phi of L dl, which is the number of galaxies per cubic megaparsec, h to the minus 3. I need an h. If I've got a megaparsec, it has to have an h on it because you don't know megaparsecs very well. The units are uncertain. We don't really know how big a megaparsec is because we don't really know what h naught is. Okay, that's not true. We know exactly how big a megaparsec is, but we don't know what the actual distance that you measured was because we have this knob that we don't know. So it's just as equivalent to say I don't know how big the unit is. That's fine. There's uncertainty. H is my uncertainty. So it's the number of galaxies per volume per luminosity. Do what I want. And it looks like this. So this is called the Schechter function because Schechter sorted this out. It's not magic. It's not actually even real. It just happens to look right. So this is like, well, that thing I've never seen before, but it looks like a duck, so we'll call it a duck. I'm sure that there are better. I've got some biologist friends. I'll come up with some good examples of that. So in biology, there are lots of examples of this looks like a perch, so I'm going to call it a perch, and then you do some bone analysis on that fish and realize it's actually something different. So anyway, so the Schechter function is this thing. So what does it look like? So phi star and L star are fiducial parameters. L star is that knee where it turns over. That's how it's defined. It's about the luminosity of the Milky Way. So L star, you can think it's where the Schechter function turns over, or you can think it's a Milky Way kind of galaxy. Both are basically equivalent. So we have this function that is basically flat. So that means that the number of galaxies in a given volume is basically constant with luminosity until about L star, and then it falls off exponentially. There aren't a lot of real big galaxies. It falls off really fast. There are a whole bunch of little galaxies. So L star is 1.2 times 10 to the 10 solar luminosities. Again, we need an H because these are now cosmological measurements. We'll do cosmology next week. So, and this number is minus 1.7, so there's a little slope to it. And phi star is 10 to the minus 2 galaxies. Galaxy doesn't get a unit. It's a number. Numbers don't have units. So this is implicitly galaxies per H inverse megaparsec. So this function looks like the luminosity to the alpha times e to the minus luminosity to the alpha. What is that? Let's talk for a second about that. So phi of L equals phi star over L star. That's just our fiducial quantity, our fiducial value. Times L over L star to the alpha. So now it's a power law on the luminosity. E to the minus L over L star. And then an exponential. So this exponential, when L is small, E to the small number is what? E to the 0 is 1. So E to the epsilon is 1. E to something small is 1. If it's something minus small, so E to the, so when L is much smaller than L star, this is E to the small number, so that's like 1. So when you're much smaller than L star, it looks like a power law. It looks like L to the alpha. So if I plot log of luminosity and log of phi and log of luminosity, I get something that goes kind of slow until I get to this L star, then it falls off really fast. And you can see that in the map. You can see that this basically doesn't do anything until L star. When L is bigger than L star, then this is substantial and small. Or bigger than, yeah, when L is smaller than L star, this doesn't do anything, and this one matters. And the Milky Way is about here. Why do they fall off so steeply? Why are there fewer bigger galaxies? Well, because it takes more crap to make bigger galaxies. So I got to evacuate a much bigger region of my uniform space. So I can't do that as many times. So just by conservation of mass, there are fewer massive galaxies. And the Schechter function, measuring it's hard. If I want the total luminosity, I would do this. So I would say the total luminosity is the integral over luminosity, L times phi of L. L times phi of L is just a distribution. So this is just getting stuff out of a distribution. So if I want the total luminosity, I just got to integrate over all the light. It turns out this works out to be a gamma function. We don't really care about gamma function. Gamma function is a generalization of the factorial. They're fun. You can do stuff with them. So this is the Schechter function. This is the Schechter function if we break it up as a function of galaxy type. So we'll come back to this functional form that's a bit up here at the top from time to time because it's a good descriptor, but it's not really right. So depending on what you are looking at, the function changes. So if I look at all of the galaxies in the local field, which is the local group of galaxies, and we're not really in a big cluster, the total looks like this. Oh, we changed units, so this brightness is increasing that way now. It was the other way before. So if we look at big elliptical galaxies, we get these guys are over here. There's fewer of them, and they're brighter than my little irregular galaxies. There's a buttload of irregular galaxies, so the density is much higher, but they're dimmer way down here. So all my irregular galaxies are over here. My spiral galaxies are here. There's a lot of them, and they're very broad. SO galaxies tend to be bigger, and there's a lot of them. Elliptical galaxies are even bigger still. So the distribution kind of depends on the galaxy type, and this is a great place for asking questions about different galaxy types. If I look at the environment, the story changes too. So this is in a big cluster versus in a void away from galaxy clusters. Galaxy clusters are like cities, and there's a whole outer space that's got nothing in it. So if you look at this is now phi is in again h inverse megaparsecs cubed per magnitude, and this is now increasing that way. So if I look at a cluster, I see that my early type, okay, there's early type mean ellipticals or spirals. Remember that Hubble wanted it to be like Pokemon, and it's backwards from the way I keep saying things actually happen. So early type are ellipticals, and late type are spirals, and it's backwards. But that's what we do. And I mean, you can't really say ellipticals for most of these because we don't know that they're ellipticals. We just know that they're reddish. Like we don't actually have good measurements of these things. So we see that in a cluster, we have way more real bright elliptical galaxies than we do spirals. But in the void, away from a cluster, we have more spirals than ellipticals, but they're all dimmer. So this whole curve is shifted to that way, so that means all of these galaxies are dimmer than these galaxies. Shifted that way. The density is lower. Duh. Because it's not in a cluster. So of course the density is lower. Because remember, phi is about a density of galaxies. So the density is lower, they're dimmer, they're not in a big galaxy cluster. The big galaxy cluster, you get more ellipticals than spirals. And then not in a galaxy cluster, you get more spirals than ellipticals. there's important physics in there that I'll talk about later when we get to clusters. Oh, if we get to clusters, I looked at the roadmap for the remaining semester, and I think I'll get through everything. Let's see. If you change units, you have to have the Jacobian DLDM. Is always true. If you change units, there's always especially in a distribution, there's always a Jacobian. Let's see. I don't care about. Okay, that is everything that I have to say about demographics. So we talked about these relationships, Tully-Fisher, fundamental plane. Those are the things that we really care most about. We talked about the Schechter function. We talked about red versus blue. I think I'm going to start the next. Does anybody have any questions about any of the stuff that I covered? I'm going to start talking about star formation. Because I'm not going to... yeah, I've got like 10 minutes left, so I'm going to just kind of mumble some lightweight stuff about where stars come from. Why are we talking about star formation? This is extragalactic astronomy, right? Stars aren't extragalactic. There's one right there. What time is it? Yeah. Right, it's right there. Stars are how we learn anything. Well, that's not really true anymore. When I started teaching this course, stars are the only way we had to learn anything. Now we have some other tools, and that's pretty cool. But really, to understand what a galaxy is doing, you have to understand its stellar spectrum. So, let's talk about star formation from the star's point of view for a second. So, stars tend to form in stars exclusively form tend to form. Stars tend to form in the galaxy. In our galaxy, stars only form in molecular clouds. They only form in clouds of gas that are like 10 Kelvin, so really butt-ass cold. And really dense. They have densities of like 1,000 particles per cubic centimeter, which is very, very dense if the average is like 5 or 10, but higher than the highest vacuum that we've ever reached on Earth. So it's still the vacuum of space, but and the gas happens to be molecular. I think it might be a coincidence that it's molecular. I think it might just be the fact that everything needs to get cold and dense before you can get stars. That's also where you get molecules. Molecules aren't necessary for the formation of the stars. Only the cold and dense is. So the molecules come with for free, but molecular clouds is where stars form. So that's how that. So you have to deal with that. So 10 to 20 Kelvin, densities of 1 to a million particles per cc, and they're very violent. The velocity in these clouds is around 10 times the speed of sound in these clouds, which is problematic because that means it makes dense things. Here's one of my favorite objects. This is M42. And you can go see M42 tonight if you want. Do you guys know how to find Orion, the constellation? So there's the 3 stars in his belt that come up over there, like that. And there's the 3 stars of his sword. And then Rigel and Bellatrix and the other 2, Betelgeuse and I always forget 2. You get the 4 stars of his shoulders and his knees, and then the stars of his sword. This is his sword. Was I smart and put up the slide I always put up? I didn't put up sorry. Let me put up the context. This one I can find because it's in basically every talk I ever give. Put it here? Yeah, here you go. So this is Betelgeuse, which we really want to blow up soon. Bellatrix, Solf and Rigel, so those are the 4 in the corner, and then the three that I always pronounce wrong, and then M42 and M43, and then this huge loop of stuff. So when you're looking at this when you're looking at this constellation tonight when you go outside, think about how big it is on the sky and how large this cloud of gas is that you can't see, but it's there. If you get a good telescope, you can see it. This is an optical image. So this big cloud of gas is the Orion Nebular Cloud. Oh, this is Bernard's Loop. And this bit here, M43, is a star-forming complex. It's not a star at all. It's a bunch of stars. So if you have a crappy telescope or a decent pair of binoculars, you can see that this is not a star. It's a big smudgy thing, and it looks just like this. It's really cool. It's very satisfying because you look at it like you look at Jupiter and it's a point, and if you're lucky, you get to see the Jupiter moons, and there's some more points, and that's actually really pretty exciting. But this is like a big fuzzy ball of stuff. Now we know from looking at the stars in this that it's at least 10 million years old. And the free fall time is 3 million years. So why is there still an object here? It should have collapsed 7 million years ago. Well, no, it's the turbulence and maybe magnetic fields. And this is what I got hired to do, is figure that out. So that's an open science question. We don't really understand why star formation is so slow. I could spend hours and hours and hours about talking about why, but I'll keep it very brief today. So the basic idea is it's actually really hard to get that much mass in a small space. Free fall is not going to collapse to a point because we don't live in a one-dimensional universe. It's kind of a nonsense idea to think that I take a sphere and it will all turn into one point without exploding in the middle, because they're all unstable. All of this gas is unstable to hydrodynamical instabilities that shred things really pretty aggressively. So this cloud of gas has hung around for a long time because of the turbulence, maybe because of the magnetic fields in the galaxy, but just between you and me, I don't think magnetic fields matter too much for star formation, even though, again, that's what I got hired to do. But let's look at some other regions. So this is the Taurus molecular cloud, which is one of my favorites. This is a radio image, or maybe this is an infrared image. I didn't write it down. I didn't write down the image credit, so jerk. So Taurus is cool because it's really dark. There are no high mass star forming regions, so you can see M41 or M42 because we have these giant OB associations. An OB association is a bunch of O stars and B stars hanging around. So we have these big OB associations. Taurus is fascinating because it doesn't have any O stars. It doesn't have any massive stars. We don't really know why, but it's forming little baby stars. So you can see it in the infrared. And you can see the magnetic fields, but I'm not going to put them up. And here's Serpens, which is another good star forming region. Can you see this stripe of gas? This stripe of cold gas? And then here's our star-forming complex in the middle. What do we have? This is Westerhout 33. I just think this one's pretty. So you can see all kinds of physics going on in here. So this is a region where there's something forming and it's blowing a bubble. This is blowing another bubble here. That's a foreground star. We've got some cavitation here. The different colors are different chemicals that we can talk about. All of these guys, W33 and Serpens and Taurus and the Orion Nebular Cloud, are all in this belt called the Gould Belt that is centered on basically the sun and has basically nothing in it. So we live in this weird part of the galaxy where we live in this region where if you go about 1,000 light years in any direction, you don't really run into anything. And then you run into all of this star formation. Really looks like something super violent happened here a couple billion years ago. We don't know what, but it was pretty violent because it caused all of this star formation. It caused an evacuation of a huge hole. And we have this massive amount of star formation in this ring that's actually really pretty close to us, which is really pretty cool. So what drives galactic spectra? The star formation. So the formation of the stars is really important because the formation is where you get the O stars, and that's how you learn stuff. And then they blow up basically immediately, and then the star formation is over. So star formation is really about O stars, and I'm gonna stop there because we're gonna. Yeah, I'm gonna stop there, and we'll pick this up on Thursday, and we'll talk about how do you make a galaxy look right. How do you make the light from a galaxy look right based on the stars?